All right, good afternoon everyone, welcome back. This is our 8th lecture on the introduction to programming with R. I'm going to wait just a couple more of minutes to let you know about something that I'm discussing with the graduate coordinator at biochemistry. So maybe some of you will be interested to know about a new course that we're planning for the fall, but also I would like to have some feedback from you, like who will be interested to take this course. So I'll let you know in just a couple of minutes when we are at 1 p.m. sharp. In the meantime, if you guys have any questions or anything that you would like to ask, please let me know. Okay, we're almost there. So what I'm planning for today is to start over where we finished last class. And again, if you guys have any questions, please let me know. Just monitoring here that everything is working. Okay, so we are at 1 p.m. So what I wanted to let you know is about this new course we are planning to have in the fall. So it's going to be a 6 weeks long course, similar to the one we are having right now, but it's going to be in Python. So instead of using R, we will be using Python as the programming language. So my question for you, and I will appreciate if you guys can let me know in the chat or by email, or maybe I post something in the forum, is how many of you will be interested in taking a course like that? And of course, there will be some overlapping with this course in the sense that I'm going to teach you also how to program in Python. But instead of talking about statistics, we are going to be starting today or more statistically driven applications. It will be more like, well, something different. We still don't really know, but something different in that regards. So we will cover learning some Python, of course, revisiting some of the main concepts in programming as we have been discussing in this course, like modularity and so on, applied to Python, but then it will take a turn into something else more suitable for Python. So R is very suitable for doing statistical analysis and those kind of things. But the truth to be told is that if you are planning to do some serious machine learning on neural networks, you may end up doing it on Python because there are way more tools there. So again, if you think that you will be interested, I would like to have more or less a sense of how many of you will be interested in a course like that. Please let me know. I think the course is going to happen independently. That's what I spoke with your graduate coordinator. So it's just more than anything to have an idea how many students we may get. And the same deal applies, right? So the same way that you are getting your credit for your degree, you are also getting the signer credits. So if you actually take that course, you probably will be able to complete one of the certificate programs on Signer. So it's a double dipping win-win situation kind of. Again, if you think that you will be interested in something like that, I would appreciate that you let me know, more than anything to have an idea so we can know if we can actually increase. So we had a class of 16 students in this course, but maybe we can increase that size to 30 or something. So, but for doing that, we need to accommodate things. So again, if you are interested in a course like that, please do let me know. Okay, I hope that you guys are able to see me. I'm going to start the sharing of my screen now, and as I say, I'm going to start again from the netcdf part that we left last class. Please let me know if you have any questions about this. The idea now is that we're going to be looking at how to implement the netcdf model. And just to revisit very quickly, the idea here is we will have objects. These objects of data are going to be mostly either vectors or high-dimensional arrays or matrices, if you want to think about them. Each of them has properties, and of course data associated and attributes, and of course there will be general attributes that you can reuse in these objects. Okay, again, please feel free to let me know if there are any questions. So I think I mentioned this. You have the feature of having units. So I just want to go directly into the code. So this code, and it will continue on the next slides, will show you how to actually create an NCDF file. And the first thing is we are going to need this NCDF4 library, and this is not part of the libraries that come with us. So you will need to do install package NCDF4. Okay, so that is loading the library so that we will be able to create the NetCDF file. Then I'm going to just pick an example, and I'm going to define some quantities just in order to create a matrix. So I'm going to define nx, which represents the number of points in the x direction in this case, and y, the number of points in the y direction, and I make it generic enough that it doesn't need to be a square matrix. Then what I'm going to create is my axis or coordinate system. So in this case, because it's a matrix and I have integers, it will go from 1 to the number of points in x. So x will have values from 1 to 10, y will have values from 1 to 5. So you can think about a tiny, small patch of a Cartesian coordinate system. And then living on top of this patch, we're going to define some quantity. In this case, it's a scalar field, meaning that there is just one value per coordinate pair of points. So let's think about temperature, pressure, whatever you want to think about. Doesn't really matter. And the matrix that we saw this in previous lectures is going to be created using matrix. And the numbers go from 1 to, in this case, 50, 10 times 5. And we will have number of rows equal to 10 and number of columns equal to 5. So it's a rectangular matrix in this case. It doesn't matter how this comes from. It's just an artificial way to create some data. Now, this is the part where the NetCDF handling, where you need to take care of the NetCDF, comes into place. Okay, just want to check that there are no people missing. Okay, and so what we're going to use is this ncdim_def, and this function allows you to basically define a dimension in the NetCDF file. So if you remember this picture, this is one of the dimensions. So in this case we have a matrix, so we will need two dimensions, one for x, one for y. If it was just an array, you will have just one dimension. A one-dimensional array, you will have just one dimension. So in this case, my x dimension is given by ncdim. This is the name, so it doesn't need to really match this because as you see it's a string, just the name. These are the units. Remember, NetCDF allows you to put units, and here is where the actual data comes from. So you can say this is a double, which means it's a floating point number, which means it's a number that can be represented by real numbers with decimal points. Even when these are integers, I could have used as integer instead, but I just decided to use as double just to show you that this type here don't necessarily need to match this type here. And this is a long name that you can provide, like my x coordinate or something. Okay. Similarly, exactly the same, but with the y quantity. So I have my two dimensions defined. Okay. First step. Second step is now creating the variable associated to the file. And very similar, instead of ncdim_def is ncbar for variable def. The name of the variable, in this case a, I'm matching the names, but they don't really need to. In this case it's unitless, but I could have said, because this is temperature, it could be Kelvin or Celsius or Fahrenheit, doesn't matter. And then comes how you determine the dimensions. And in this case the dimensions is a list, it's two objects, x and y. So in this case xdim and ydim that we just defined above. Okay, so this is the preparation. We haven't put any data yet in the file or even in the variables associated to it. We just basically define the vessel, the containment of where the data is going to live. Okay, any questions about this? Okay, So now this is the continuation. This is still part, if this was a function, it's still part of the function that creates the netcdf file. So this is where I put the data into the actual, I think I'm missing something, by the way. So there should be an NC out. I think my slide cutted that out. That's already done to see. Yeah, so I let me sorry about that. I think my slide, I didn't realize about that. So I'm going to show you the actual code. So you're seeing my slides, my directory. So you will actually see the code. I think yeah, sorry about that. So this line got cut out from the slides. I think I didn't realize about that. So there is a missing line there in the slides. I will fix it later. But this, so after a definition where you create the variable, there is the NCOut line. So this is a variable, and NCCreate basically is the function from netcdf that allows you to create the file. So in this case, my file is going to be named test.nc. And adif is the definition of the variable I want to put, and then force version 4 equal true allow you to specify that the netcdf file that you want to create is going to be version 4 or above. Okay, so you keep this as it is, and you just put here the variable you want to say. Now, in the assignment, I have an optional part that if you want to try is going to be really good, I think, and it gives you some bonus marks. It's like 25% more. You will need to say more than one object. So in the same way that you will do a list here, if you want to include more than one object, you will do a list of the objects here that you want to add. Okay, so that's just to let you know. So let me go back to the slides. Apologies about that. So the NCOut is the place where you define, where you create your file and you associate to it. Okay, so let me go back to the slides. Any questions about that? I'm really sorry about that. This was probably cut out here and I didn't realize. So now is where we define this NCOut. So this is the handler of the file. We talked about this last class. We define the handler of the file, and then we just decide what to put there. Okay, and as I say, if you have more than one, you will do a list of these objects. Okay, now remember the attributes, the global attributes. You do that with NC attributes put, and then you define again the name, the placeholder of the file, and then 0. Don't worry about that, but there's some way to create the dimensions. You just can keep it 0, so it's very, very basic. It's a global attribute, otherwise you can enumerate the different objects, but 0 represents the whole object, the whole file. So here, for instance, says title, my JSON data, and then institution signed. And this is very important. At the end of the function, you need to close the file. So NC close, and the handler of the file closes the file. We saw this as well last class. Okay. Any questions about this? Okay. So, how we read files? So in the same way that we need to use NCDF4 for writing files, we will use it for reading. And now instead of NCCreate, we are going to use NCOpen, the name of the file, and we assign this to a new variable NCIn. And basically, then you can print NCIn and then inspect all the metadata. Remember, these formats allow you to keep metadata associated, so this metadata is all displayed for you, and then you can dig deeper. Basically, it will behave more or less like a list kind of. So this is the very basic of how you will read. It's very easy to read to actually get information. Okay, and on top of that, let me see if I can show you that. On top of that, let me see if I have my text example here. I think I mentioned this to you. So this is my, I don't hope you can actually see this. So this is my script in R that writes the file, and this is the actual file, the test.nc. Turns out that in the terminal, you will need to install this. There is this ncdump command that allows you to inspect the file. So I can do ncdump, And basically it provides me with information about what it contains. So the dimensions, in this case, as we discussed, x10, y5, what type of units there are, they have, the units of A, if you were, this is unitless as we define, the global attributes that we wrote, and the actual values of the quantities x, y, and the matrix itself. Okay, so again, this is very handy. HD5, for instance, has also a visualization tool, just to show you that it's a very convenient format to store your data. Okay, any questions about this? So this is just to show you, if you want to actually access from R the actual values of the variables. So I'm going to define X, and I'm going to use NC bar instead of put get from the handler of the file, and now the name of the variable. Of course, if you don't know that, if you don't know how the variables were called, well, that's why you look at the NCIN information, right? So it tells you which are the name of the variables, excuse me, the matrix general object A, then the variables X and Y are defined for you, it tells you the dimensions. So all these things are accessible. And again, NCIN is a sort of complex list. So you can actually, even when you print this, you can actually get this information as bracket notation as well. So you can automatize this if you wish. So NC bar get, NCIN X, give you the information for X, and similarly for the matrix A, and then you can get the dimensions, and all the functions that we can use are available. You can also get the attributes. So again, the 0 represents a global attribute in the file, and then what kind of field are you looking for? Okay. Again, any questions about this? I have more information. I told you this is my summary. We discussed most of the things last class. I'm not going to keep hammering you with this, but the important part for today, in particular, if you want to try in the assignment, is this part, how you create the netcdf file. These two slides, I'm going to fix this one, sorry about that. And again, if you want to try it for the assignment, I think it's going to be a good exercise. But more importantly, I think I told you this is like the best probably approach for saving your data in a very professional manner. So any person looking at your code and seeing that you are handling your data with netcdf files, you say, okay, this is a professional code. This is up to the very highest standards in the field. So my strong recommendation is, whenever it's possible and whenever your data fits the model of netcdf, then it's a good idea to give it a try. You won't regret, I promise you. Okay? Any questions about this? And as I say, I have a bunch more of other information, like I told you about this, the text encoding for different languages, some examples that you can follow along if you're interested or ask me, and then a little bit of information about HDFI. HDFI is super useful, super powerful file format, very similar to netcdf, but way more generic. So you are able to store all kind of information there. I don't want to cover that because it will take me like probably 1 or 2 lectures just to discuss this, but just to give you an idea of how it works. Okay, and that's basically it. So any questions about this? I'm going to be switching to the new set of slides, but please do let me know if you have any questions. Take a quick look at the chat. Just to be sure. Okay. So everyone looks to be very quiet today. I hope that I'm not boring you too much. And again, remember, if you are interested in this Python course that we may have in the fall, please let me know just in the chat or by email. I would really appreciate having a little bit of feedback about that. So, so the plan for the rest of the class today is to discuss a little bit of the basics of computational statistics. And again, I don't really know how much background you guys have in statistics. I hope that you have taken at least some introductory courses in statistics, and why not probability as well. I usually, when I teach the longer course, I spend at least one lecture and a half just reviewing the basic concepts, because this course is smaller and it's not necessarily aimed to this. I'm going to skip that part, and I'm going to just go into showing you how to do things in R. But again, I would strongly recommend, depending on what type of research you do, to take a look at that. Now, what else I want to say? Oh, yes, the other thing is, so we do this in particular because R is very well suited for dealing with statistics. R is if you look at the definition of R as a language, is a project aimed to handle and help with statistical analysis. So that's the whole, or the real reason for our existence. So that is why it's so compelling to do this kind of analysis, of statistical analysis in R. So we're going to just start by looking at what we call descriptive statistics. That's quantities that allow you to compute different, it's called estimators in the formal language, or jargon, or statistical jargon, estimators for different observations. So R provides a wide range of functions for obtaining summary statistics. The summary function is one of them. Other functions that you may find are mean, standard deviation, variance, minimum, maximum range, quantile, fine numbers. Each of them are very easy to use. If you look at any of the data sets that R brings as well along, you can see that you can very easily grab any of those, like their passengers data, for instance, apply the function, it will report you back some data, and all kind of goodies are there. Okay. Again, I usually spend some time explaining the difference between the different estimators, but I'm not going to do that in this case. If you have any questions, though, please do ask. Okay, let me know. So all these functions are accessible and available right away for you to use. Okay. Now, one of the things that you should know about R is that not only bring these descriptive statistical functions already available, but also many a long list of probability distribution functions. And this is a list probably not complete by now, but you will find functions like the uniform distribution, normal distribution, binomial distribution, Poisson distribution, beta distribution, Cauchy distribution, chi-square distribution, long list of them. Okay, and if there are a particular distribution that you use and it's not here, I bet you there is a package already that implements that for you. Okay, now one of the, or among the most useful ones or important ones, let me see, I think I have questions. Some of them they do. So Larmia is asking if some of the functions apply to data frame, and the answer is yes, some of them they do. Most of them they do indeed. So if you are asking in particular to about the descriptive statistical estimators like summary, yes they do. Okay, these ones we are going to be discussing now, the standard distribution functions and the related associated ones, no, are more like numeric types. But the previous one I was mentioning, yes, they do. If you have any particular example in mind, please let me know. We're happy to discuss that as well. Okay. So for these statistical distribution functions, now, for instance, you want to have a uniform distribution, which, you know, the uniform distribution is basically the same distribution independent of the value. This is defined by the range between A and B being the limits of the distribution, and the keyword in R is unif. For normal or Gaussian distribution with a mean and a standard deviation, then norm is the one. Binomial distribution takes two arguments, N and P, and is binom. Poisson distributions takes just a mean value and is plus. Now, this is the very important thing to remember for now. For every single distribution function defined in R, there are 4 associated functions, 4 related functions for that given distribution. One is the actually probability distribution function or density distribution function. Another one is the cumulative distribution function, or what we actually call probability. Then we have the quantile function. And then, this is one of the most useful ones, be careful and pay attention, is the random number generator function. Okay, so let me just open a parenthesis. Okay, before that, so let's say I'm looking at the normal distribution function. So the function is named norm. Now, if I want the density distribution function, I will do dnorm. If I want the cumulative distribution function, meaning the probability, I will do pnorm. The quantile function qnorm, and the random number generation given by a normal distribution function rnorm. Okay, this is very important because when people usually work with random numbers, and the assignment today will be about that, and very powerful and important techniques in computer science and computational statistics are based on that. One thing that one need to bear in mind is that the numbers that are being sampled come from a given distribution function. Okay, so usually if nothing is said, usually it's used the normal or Gaussian distribution function, but one could sample numbers from different distribution functions. Okay, again, very important point. Let me know if you have any questions. Some examples. Okay, let's say I want to have density values from the normal distribution function with a mean of 0 and a standard deviation of 1, and I want three possible values. Then what I will do is I will do dnorm, and I'm passing a vector where I'm going to just evaluate in the normal distribution function as the value -2, 0, and 2. And as you can see, I'm not surprised there, the normal distribution function centered at 0 with a standard deviation of 1 is symmetric, means that the -2 value and the 2 value are the same. If I want to shift my normal distribution function, I usually put a plot of the normal distribution function, but it's the typical Gaussian. I want to shift to a mean of 1 and standard deviation of 2, and then I ask for the same values. Now you can see that that symmetry is broken. So the distribution now is no more symmetric because I basically shifted the value, and now because I shifted by 1, the symmetry is between 0 and 2 and not -2 and 2. Okay? Now if I want to compute the quantile, so the quantile you can think of as the opposite operation of the probability, meaning like if I gave you the quantile of, in this case, 0.25%, 2.5%, then I will get a which value of x, the probability is 2.5%, and that's exactly what the quantile returns me here. Okay? If I actually want the probability values for a series of numbers, now I can just do C, and when I don't specify anything else, like here, here, or here, R by default is going to assume that the mean is at 0, meaning the Gaussian is centered, and the standard deviation is 1. Okay? Any questions about this? Again, I usually spend way more time putting this in context of type of probability question, statistical questions. If you want, I can add that as an appendix to the lecture. But again, because this course is not necessarily aimed at that, I just want to show you the functionality available in the functions in R. Okay? So, generations of random samples. Again, this is going to be the important part for the assignment this week. If I want to generate 5 random numbers from the default normal distribution, instead of using dnorm, or instead of using qnorm, or instead of using pnorm, the function I had to use is rnorm. Okay, this is a typical mistake or misconception that we have every time I teach this. The random numbers come from the rnorm function, not the dnorm function, not the qnorm function, not the pnorm, from the rnorm function. And the parameters that you pass is how many of these guys you want, how many random samples you want to generate. So if I want 5 random samples, then rnorm 5 is what you want, and the function will return you 5 random numbers. If you want 5 random numbers coming from a specific function, from a specific distribution, the normal distribution centered at 0 with a standard deviation of 50, then you need to specify that, because by default R will assume centered at 0 and a standard deviation of 1. Okay, just to show you one more example about this, if I want instead 5 random numbers taken or drawn from a Poisson distribution with a lambda value of 100, then I had to use, instead of rnorm, I had to use rpos, because that gave you the 5 random numbers coming from the Poisson distribution, not the normal distribution. And something to notice, and again, this I will spend more time explaining in a different type of course, but the Poisson distribution is what we call a discrete probability distribution function, while the normal distribution is a continuous. So it generates continuous values, real values, like decimal points numbers, while the Poisson generates integers. Basically, you describe events like phone calls, traffic accidents, something heuristic like that in counts using a Poisson distribution. Okay, any questions about this? Take a look at the chat just to be, usually blinks if there is any questions. Let me know if it was clear, the explanation, or that was what you were asking. So, if you have no more questions, I'm going to cover another of the very important topics. Okay, so let's see. Perfect. So this is another important topic, and I'm going to merge it with statistics. So it will contain a little bit of statistics, a little bit of data analysis or data manipulation, or data processing if you wish, and performance. So it turns out we discussed a couple of lectures, maybe a week ago now, or more than a week ago, we discussed how to repeat things in the computing by using loops, right? And we look at the for loop, and then we discuss also vectorization and slicing. And when you do that, it's way more powerful because R does it in a very efficient manner. Well, this applied family of functions has the same at its core. So the main idea of this is to avoid doing for loops or loops of any kind, and instead using these applied family functions. And we're going to see how they work. And I say there are a family of them because there are different ones depending on the objects or the type of data you would like to use these apply functions to. So for instance, lapply is a function to apply to each of the elements of a list of a vector. So think about this. If I have a vector and I want to loop over each of the elements, I will do for I in the vector and then do whatever I want to do in the body of the for loop. Instead of that, you can just call a function, lapply, and define what you want to do in each of the elements, and that is it. So it's way faster, it's optimized, and also it's cleaner code. So you will see how useful, how transparent it is. Sapply is the same idea of lapply, and I will show you an example. The idea here is that it will simplify the return, and instead of returning a list, it will return a vector. And you will see in a second why this is useful. Apply, same idea, but it can be used to with matrices or high dimensional arrays. Tapply is for a subset of elements in a vector, and napply is one of the most generic ones. It applies to anything basically, and it receives multiple arguments. So I'm not really going to show you that, but this is one to keep in your mind because it's super powerful. And I think I have a question. Yes. You can exclude NAs, so there is a way to basically purge the NAs or nuns in a particular case. Yes, good question. So I think I jump ahead in my. So these bullets on the top, you can actually click on them and it takes you to different slides. So let's take a look at the lapply function. Okay, and as I tell you, it takes a vector or a list and applies whatever you want to do to each of the elements. So let's say that we wanted to have, so we want to show that n grows larger. As n grows larger, the mean of a given normally distributed random numbers tends to 0. And the reason is, the mathematical reason for this is that if I have random numbers that are taken from a normal distribution, which is centered at 0, I should say that the law of what is called the law of the large numbers in statistics is sort of a theorem, if you ask, is it tells you that the distribution, the mean estimator for the distribution of these numbers will converge to the actual mean of the distribution. Don't worry about that, that's the justification for this example. But in any case, I'm going to define a function called mean nr norm, and what this function is going to take is going to take a number n, okay, and it's going to return the mean of n random number sample. Okay, so I say give me one number, and the function goes samples one random number from the normal distribution. Because I'm not specifying the parameters, it's going to take the default values, centered at 0, standard deviation 1, compute the mean, return that. If I say 10, it will go take 10 random numbers, compute the mean of these 10 random numbers, and return that. Okay, it's a clear, very simple function, one line function. I didn't use the curly braces I usually do, but because to make it fit in the slide, I prefer to do it that way. Okay, now how could I explore what will happen if I increase n? So I could do clearly a for loop here for I in 1 to 10 million every 1,000, apply this function, and that will be a for loop implementation. What is the alternative here? Well, the alternative is I'm going to create what I'm going to call a sample vector containing how many numbers I want the function to use to compute the mean. So it will have one number, 10, 100, 1,000, and 100,000 numbers. And then instead of using my for loop, so I could do for I in ns and then call the function inside the for loop, I could use my lapply function. So lapply takes the following form. It's the lapply function. It transfers the vector that you want to apply the function to each of these elements, because that's how you will do it. You will take this function and apply to each of these elements, and then the name of the function. Okay, that's simple. If you do this in that way, this is what it outputs. And remember, it's lapply, so it's going to return a list. So that's why you will see the bracket notation following by the bracket notation. So this first element of the list, which is just a number, second element, third element. So what you see here is this mean.n unknown function applied to one number, applied to 10 numbers, 100 numbers. So n is 10, 100, 1,000, and 100,000. And as I was mentioning at the beginning, because this comes from the standard normal distribution centered at 0, you see that the mean is conversion to the value of 0. And again, the responsible for this is the law of the large numbers in statistics. Any questions about this? This is crucial that you understand not only what you're seeing here, the values, but you understand the mechanism in which the lapply function works. This is a vector. Each of the elements in the vector is going to be used as the argument of the function that we want to write in the second part, and that's how it goes. And it's an alternative method, way better method than just looping over the elements of this vector. I'm just pausing here on purpose just to see if you guys have any questions or anything is not clear. Okay, so show you a different way to obtain the same result by using 2 times lapply. So I had the same ns vector, the same number of samples vector as before, and then what I'm going to do is, instead of using my function as I defined before, because as you can see, my function uses the unknown function inside and then the mean function. So instead, I could actually implement this in 2 steps of lapply. So that's what I want to show you. Okay, so this is how can I use lapply for the functions that needs 2 or more arguments? Great question, great question. There are a couple of ways. This is an amazing question. I used to have an assignment that requires that. I don't remember if this assignment, I don't think this assignment requires that, but there are 2 ways, two basic ways. First way is to define what we call a wrapper function. What is a wrapper function? So let's say that my function here, instead of receiving n, it will receive also m. So 2 arguments, okay? While m was the mean of the standard distribution. So if I want to use lapply, then I need to define an additional function where I'm going to put the value of m I want to use. So in this case, I will have mean2, and mean2 will have the actual value of m, and it will call this function with the value of m. So for mean2, there is only one argument instead. Okay, so one option is define a wrapper function. The other option, so let me write that in the chat because it's a really good question. One option is a wrapper function. Second is to use mapply. So mapply, I told you, is one of the super powerful apply functions, and it also allows you to do multiple argument functions. But it's not as trivial as just writing the function name and then the argument. You need to write the vector, function name, comma, and then the arguments that you want to use. Okay, but it's a really, really good point. Thank you for asking. And let me know if something is not clear or needs more clarification, okay? In the meanwhile, I'm going back to this example. So in this case, let me see. Perfect. But again, I'm happy to discuss this a little bit further if you want, because it has details involved, and it's a very important point, by the way. Thank you. So in this case, I'm going to first, because I want to store and see what random numbers were generated. Here in my previous function is hidden, right? The random numbers, are generated. The mean is computed right away, and that's it. I missed information. I lost information of the random numbers that were generated. So in this approach, I'm generating random numbers by using lapply. ns is my vector, and then our norm here is taking each of these elements as the input. So this will generate a list with 5 entries, and each entry will have 1, 10, 100, 1,000, and 100,000 elements in each of the entries of the list. Okay, again, try this example and try to see that. This is very interesting, I would say. Now, if I want to obtain the means again, well, I apply random numbers and the mean. And because it will apply to each of the elements in the list, now each of the elements on the list are vectors, it will basically apply the mean to each of the entries. And you can see, by looking at the result, you can see a similar trend. Of course, the numbers don't necessarily match because these are random numbers, they change all the time, but you can see the same trend. It's converging to 0, which is the expected value, the mean expected value for this distribution. Okay? Same example, same result by the end, but a different implementation by using 2 times lapply. Okay, any questions about this? Okay, let's take a look at sapply. Sapply is very, very similar to lapply. The only difference is that the result that is returned, instead of being in a list format, is in a vector. So I'm going to show again my sample vectors, 1 to 100,000. My random numbers generated by lapply, exactly the same example as before, but now the means, instead of computing with lapply, I will compute with sapply. So sapply of my random numbers and the mean. So that's the only thing that changes from before. And now if I look at my means vector, now it's a vector, no more a list, you can see that these are elements of a vector. These are just the numbers from the vector. Before, they were in a list format. What is the advantage of having them as a vector? Now I can perfectly operate with different mathematical functions, like multiply them and compute things. So that's the advantage of sapply versus lapply. In this case, notice though that I still need to do this intermediate step with lapply, because I will have basically vectors with different length. So they had to be, remember, vectors had to be homogeneous. So the list, which allow you to have heterogeneous types, will be the perfect container for this variable. Okay? Any questions about this? Okay. So there is another version of sapply called bapply, and this is, again, we are touching upon the bleeding edge, the top of things here, right? This you will do when you are dealing with very large vectors, right? And in my examples, these are just a few elements. Even 100,000 is relatively small. But when you have a matrix representing a complex atomic system or molecules, and these are 100,000 or million of elements or more, then things start to matter in terms of performance and memory optimization and memory utilization. So instead of using sapply, one advantage of using bapply is that you can pass into the function the object as a third argument, where the data is going to be stored. Why this is useful? Because it can be substantially faster and more memory efficient for large output. It's because you already allocate. So we saw this when we were talking about vectors. If you remember that lecture, that one way to increase, so there are different ways you can increase the size of a vector or add new elements, but one way is to initialize with a very large number of elements and put them to 0 or something. So if you do that, then you can use bapply, and by doing that you will get in performance. Otherwise R will have to create this vector on the fly. It doesn't really matter the technical details, is that is better in terms of memory utilization and performance in terms of how fast it will run. Okay, just to let you know, a third type of apply function. Let's go to the apply function, which basically can be used for matrices or high dimensional arrays. And the apply function, because it allow you to do that, then it will have one more argument to be indicated, which is called margin, and it can has the value 1 or 2, or actually 1 and 2, and what it tells you if it is going to apply the function by rows or by columns. So let's take the example of a matrix from the 3 by 3 with values from 1 to 9. So this is how the matrix looks like. And now let's apply, for instance, let's say I want to compute the maximum of each row. So again, if I had to do this in a for loop manner, or how I will do it is I go to row 1 and I say what is the maximum value here. Okay, 7, row 2, 8, row 3, 9, right? And go row by row. I could do it with a for loop and slicing and then applying the max function. Look at this, just one line, right? Apply to the object A, that's my matrix. Margin 1 means apply per row, and then the function I want to apply, the maximum. And that's it. Boom, you get the 3 maximums right away. If you want by column, you do margin equal to matrix A, margin 2, maximum, and you get the maximums for each of the columns. Okay. Another example, so same matrix A, and I show you how to do margin 1, 2. This applies to each of the elements. And this is a little bit forced example. So there are a couple of interesting elements here though. So apply in the same way A, the matrix. Margin 1, 2 applies, so per row and per column, that's what it means. This is the vector 1, 2, nothing else. I could have written C1, 2, and that will be exactly the same. And this is one of the new things. So this is what we call inline function definition. I usually don't like to do this, and the reason is when you do this, you can use this function only here. As you can see, it's the usual way we define a function, but there is no name associated to that. So what R knows is, okay, this function takes one argument x, takes the element, powers to the power of 2, and that's it. That function exists and lives only there. It's a quick solution when you use this only once. Otherwise, I will recommend always define my square function or something somewhere else and then call it here in that way as the max function, but my square function. And what this function does, it takes each of the elements here and takes the power of 2. So 1, 4, and so on. Now with matrices, we saw that many of the operations works in an element by element basis. So this is maybe redundant. So you might not need to do that by just doing A star star 2, it will just work. But it can show you that you can take any other operation that you may want to, okay, any other function that you would like to define. Okay, so that's how the apply function works. Any questions about this? Okay, one more for the family, tapply. So tapply is very useful, and I think one of you were asking about statistical functions applied to data frames. This one applies to data frames, super useful for data frames, super powerful for data frames. Excuse me. So the apply function applies to a cell of rag arrays. So basically a subset of a data frame. Okay. And how does it work? So let's take another data set from the R examples data sets. In this case, it's called Morley. So Morley is basically the Michelson-Morley experiment. Remember, for measuring the speed of light in vacuum or the ether in that case. So historically, the Michelson-Morley experiment tried to demonstrate if the light was traveling at different speeds. A different speed either in vacuum or in this supposedly medium ether. So that was to basically boil down that, to break down that hypothesis and basically give a backup for the special relativity theory of Albert Einstein. Doesn't matter the content. The point is that this data represents the measurements of the speed of light and repetitions and different experiments. So if you look at the structure of, so I assign Morley to my data frame called data. And if I look at the structure of it, it has three variables: experiment, run, and then speed measured. I think it's in miles per hour or something like that. And then there are 100 of observations of this. So there is experiment number 1, and then 10 runs of experiment number 1, and then there are experiment number 2 and X runs. I think there are 5 experiments. And let's say we want to compute in this case, so within each experiment there are different number of runs that you will run the experiment, because this may be, so the measurement may be affected by, you know, the conditions of that day in the lab, or the state of the laser being used, or whatever. So what happens is you run several times the experiment in a given condition, and then you repeat the experiment another day, or with a slightly different configuration or something. So you end up having and let me see if we can actually see the data. So if I do Morley, sorry, this is to R. If I do Morley here, you will see, so there are the runs, so the experiment, so experiment 1, run, experiment 2, number of runs, and so on, and the measures for each times of the speed of light. Okay, so question being is, how can I get the mean values for each of the experiments that we run? So t-apply will help with that. So what I'm going to do is I'm going to say I want to compute for the speed, so from the data frame, which I call data here, given by the column speed, segregated or aggregated or considered by type of experiment, and the function I want to apply. So what that returns is, for each of the experiments, it gives me the mean value of the speed. So it's a very nice and quick way to compare that. We're going to see in the visualization part how to do this in a very graphic manner. Now, a similar result can be obtained by using a split. And a split that basically does is it takes data and divides the data into different groups. So if I show you this here, if I do a split of Morley speed by Morley experiment, that will give me basically 5 different vectors that are, or 5 different lists in this case, that are segregated or differentiated by the experiment number 1, 2, 3, 4, and 5. And then what I had to do is compute the mean on those. But that's basically the idea here. You are able to aggregate the data by looking at a particular feature of the data, in this case the number of the experiment, and then apply one of the functions to that. Again, if you're going to do this by hand with a for loop, you could do it, right? You could go and slice the data frame by the experiment number and then apply the thing. But look, this is done in one line. It's efficient, it's fast, it's clean, it's just one line, right? So I will encourage to, whenever it's possible, use this kind of features or functions. Okay. Any questions about this? I have another example of the apply function just in a sec. So this is another example. This is for another data set, also part of the R data sets. It's called DNAs, and it's nothing else that an ELISA array for recombinant protein DNAs. And the idea here is, if you look at this data set, it has again 3 different values, I believe, or 3 different values, and 176 observations, and then there is run, and then there is the concentration and the density. So it turns out that you measure the concentration of the protein by looking at the density and how it reflects light. So if you look at the actual data, it looks very similar to the Microsoft Morley experiment data. You had a run, you had the concentration, and then the density. Now the control variable here is the concentration. So you set or prepare the protein with different concentrations, and then you measure the density by using light on it, or shedding light on it. So let's consider that we want to compute the mean and the standard deviation of the optical density measurements for a given value of the concentration. I told you, if you look at the data, if you do DNS, you will see that the values that repeat, the values that you control, are the concentrations. So you want to measure the dispersion in the values in the density, which is the quantity that you are measuring here. So we can do the same trick as before. We can use tapply for the density. That's what we want to compute, the mean values, separated by concentration values. So if you do that, then you obtain for each of the concentration values the corresponding mean values of the density. And similarly for the standard deviation. The only thing I change here is to use the standard deviation instead of the mean function. Okay. So again, very useful, very quick way to analyze the data in a very, very efficient manner. Okay. Any questions about this? Okay, so that's all what I have for the apply functions, and that's perfect time for stopping and discussing the assignment, because all what you will need for this assignment are random number generation, something that we discussed at the beginning, apply functions, something that we just finished discussing, and if you decide to do the bonus part, the netcdf file, that's something that we also discussed at the very beginning of today's lecture. Okay, next week we are going to start over here discussing statistical modeling, and again I will really appreciate if you guys can let me know how much interest you have in this topic. Otherwise I will just cover whatever is in the slide so you can see what I have planned for the class, and then we are going to move into visualization. But if you would like to discuss more about models, we can do an additional class on model diagnostics. But again, please let me know. And again, if you had the chance to let me know what your feeling is about this fall course on learning Python, it's going to be valuable information for me and for the graduate coordinator. So I appreciate if you can let me know. So let me talk about the assignment now. See, so this is assignment 4. Okay. So I have a quick comment on the Python. Yes, please, Dorna, please go for it. I think the course will be very interesting. Haha, okay. I will raise at this point with the graduate coordinator. I actually did it yesterday, and he has an explanation why they like the quarter credit system. But I will be happy. So you know what, guys? If all of you agree, please, I will be more than happy to raise this point. Okay, awesome. So this is I promise you. You know what? I will raise this point. I had to email Alex Palazzo, is your graduate coordinator, by the way. If you can also let him know. I think some of you may be directly related to him in the sense that you work with him or something. Please let him know. Because I couldn't agree more, and that's the other thing. If you think that the workload is too much, I asked him also to run a survey at the end of the course. He told me they usually do that with these courses. But if you feel that I'm pressing you too much with the material and the assignments, this is for the first time for me teaching in your department. And each department has its own way of doing things, so I will trust in what you tell me about that. If you think that this is a lot for your type of courses, I'm happy to take your word for it and slow down things a little bit. Okay, so I will be more than happy to start a conversation about that and do something right away, like maybe this assignment we can take it, if you think this assignment in particular is too long. I think it's a very nice assignment because it shows like a lot of really good points in research. But if you think that it may require more time, please do let me know. And to be honest with you, because I have been seeing that you saw that I try to evaluate your assignments as soon as I can, right? And I have seen that you guys are doing really well. So I have been cranking up slightly each assignment, right? Assignment 1 was quite simple, straightforward. Assignment 2 has a little bit more. Assignment 3, I think you noticed there was a little bit more. And this assignment, to be honest, it has even a little bit more, and even I add an optional part. So yes, I please do let me know those kind of things. I ask you for your feedback. I try to adjust things as we go. It has the disadvantage that I cannot see your reaction, your faces right away. Otherwise, I will be reading that. but because the course is fully online, that part is missing, right? So I need you to communicate with me in whatever way you prefer. You can start a post in the forum. The environment, I hope, in the course is friendly enough that you feel comfortable talking about these things. Okay, I'm not going to take it back on you. Quite the contrary, I actually will appreciate all the feedback that you can give me. Right away, what I'm reading is that you guys are investing a lot of time, and I respect that, and I take that, and I know that in this particular situation, in the times that we are living, being at home is complicated and doesn't wait as much as one would like in the sense of spending time. So maybe we can do that. Maybe this assignment can be for not 1 week, but 1.5 weeks or 2 weeks. Let me know about that, okay? And I do agree with some of you that the assignments is a great opportunity for learning. We don't have midterm, we don't have final. So the only way for you, or the only chance for you to practice these concepts are the assignments. And the idea here, and again, you may notice or not this, but I always try to put some additional things so that you can learn a little bit more than what we just discussed in class, right? So the assignment for me are designed in two manners. One is to practice the things we discuss in class, and the other is to always give you a take-home message from the assignment itself, okay? But yeah, please do let me know all these things, okay? And let's do that. Let's do this assignment for 2 weeks, okay? It sounds reasonable for everyone. So instead of being due on the 14th, we do it on the 21st, and then we adjust the other assignments. I was supposed to have, I think, 6 assignments, but I will be happy with 5 assignments instead. So we have this assignment and 1 more to go. Sounds good? Sounds good to everyone? Okay. So let me tell you very quickly. I think we are a little bit over. We're at 2 p.m., but let me just in 5 minutes try to summarize this. No, my pleasure. This assignment for you. So this assignment is very. I like it very much. The framing. It can be a little bit. Intimidating, because it's very verbose, so it has a lot of description, but it tries to guide you again through all the things, right? And the technique I want to practice here is one of the most powerful techniques in computational methods. It has even won awards in last century, in the 19th century, in the 20th century, sorry, because of being one of the most useful techniques in computations. And this is called Monte Carlo methods. And the technique that has awarded these prizes is called Markov chain Monte Carlo, but this is a variant on this technique that we are going to describe in this assignment. It's a more simple manner, but more simple application. But again, you can read the description, and again, feel free to ask questions if something is not clear. And the idea here is that we are going to apply for a method to probabilistically determine when a rugby player may get a concussion or not, okay? And this is based, so I read this couple of papers and I got inspired, and I say, okay, let's do this. Let's pretend, and this is a very simple model, so nothing quite close to reality, I would say, but let's pretend that we can determine with certain precision or the certain certainty when a rugby player may get a concussion. And this will be given by 2 probability distributions. One probability distribution is a Poisson distribution. As I mentioned today, this is a discrete distribution, and this will model how many games in a season a rugby player may play. And let's say the average, and this is giving you a parameter for the distribution. The Poisson distribution has only one parameter, is 25 games per season. The other parameter that will determine if a rugby player will get a concussion or not is when a rugby player is tackled, is the momentum of the other player tackling the rugby player. So if I have someone tackling at me and it has a momentum given by a threshold or beyond a given threshold, the tackling is going to be very, very violent, and it may hit me bad, right? So the idea here is that if a tackler with a given momentum has a threshold, or the values given above a given threshold, in this case it's exponential distribution with a rate of 5 in dimensionless units, then if it goes beyond that, then it's very likely we'll get a concussion. Now, the 2 facts together, the number of games that a player or a regular plays during the season, and the momentum of the tackles that that player receives is what conforms the final probability distribution of actually getting a concussion or not. Okay, this is described in a way better manner here. I just want to give you the whole picture. So what we are going to do for modeling this, and this is just the context, right? You can completely isolate about that, forget about the rugby or the player or whatever, and just follow this part. So we are going to create a file named myPDF, so my probability distribution functions.r. This is one of your utility files. It will have three functions there. One function which is called sampling games, and this function will basically randomly generate, and this is where the random numbers come into place, will randomly generate from a Poisson distribution with the specific mean that was discussed here, a vector with n random samples. So the function will receive n as one of the arguments. It will, two arguments, n, and then an optional argument with a default value of 25. That's the mean for the Poisson distribution. And it will return a vector with those random numbers. Okay, very simple function. Just read it carefully, revisit the slides where we generate the random number, and that's it. A second function called sampling tacklers, which will generate and return n samples drawn from an exponential distribution with a specific rate. And again, it will receive two arguments, n indicating how many samples we want to generate, and then an optional argument indicating the rate of the distribution used for this value, okay, and the default value of 5. The third function is a function called simulate probability of conclusion, which basically use the previous two functions, okay, and it will receive three arguments, this function. One number n representing the number of samples, which we will then use with the other functions. An optional argument determine the minimum number of games, is called threshold games, at which a player will suffer a concussion. So the default argument is, the default value for this variable is 20, and another optional argument to determine the minimum momentum of a tackler, threshold of tackler, for which a rugby player may suffer a concussion. The default value in this case is 0.2. So this is what the function will do. It will generate n random numbers for the games, n random numbers for the value of the momentums of the tacklers, and of course using the previous defined functions. It will store these values in a data frame, and then it will compute the probability of the likelihood of the concussion by considering the number of cases where the number of games is greater than the threshold of games, and this is important, there is an and there, the tacklers where the momentum of the tackler was greater than the threshold of the tackler. Okay, and this is what the Monte Carlo technique is all about: is generating random samples and then counting them by a given condition, a given constraint. This technique is used all over the place, from genetic evolution up to measuring integrals in high dimension, or many different things. Okay, so this is your utility file. Okay, I know it feels and looks a little bit overwhelming, but believe me, you go step by step, it's simpler than what it actually looks at the beginning. Now, so that's one file. I want you to create a second file called concussion.mc for concussion Monte Carlo.r that will do the following. It will source your utility myPDF file. It will source this auxiliary file that I make available for you here, so you can see this is an R script I created for you. It's a utility file. It's a utility files for visualizing this, because we haven't done visualization. So this file defines a function called plotmc, and I show you in a second what it returns. But basically what you need to do is right click here and save it in the same directory that you're going to put your other files, so that the function can be sourced. So you will source this file and you can use the plotmc function. All right, so source these two files and then create a vector with values, with numbers of samples going from 1,000 to 1,000,000. Okay, in a step of 1,000. It's going to be a long vector, So start 1,000, go up to 1,000,000 every 1,000. So 1,000, 2,000, 3,000, 4,000, 10,000, 10,000, 11,000, 12,000, and so on up to 1,000,000. So it's going to have a lot of numbers. Okay. What I want then is to use one of the applied family of the applied functions we discussed today for computing the probability of a concussion for each of the cases from this vector. Okay, and you should store this in a vector or in a new variable, and then use the plotmc function for visualizing your results. And what you will see is something like this. So the plotmc function will take two arguments. Look at the help. Yeah, I think it's well documented there, but basically you will provide the number of samples, the vector, and the probabilities obtained, and it will basically show you how the probability changes with the sample size. And what you will expect to see is some plot like this, where basically the values converge to the actual value of the probability. And that is the value that you expect to see or you expect to get for the probability of a rugby player of getting a concussion, given all the assumptions we had done. Similarly, we'll draw you a histogram, but we're going to talk more about this in next week, actually, when we do the visualization part. In any case, I want you to take a look at this and try to interpret what the results are, okay? And you can put a comment or something, nothing too profound, to be honest with you. All right? This is the optional part, which gives you 25% extra marks. And it says create a utilities io.r file which contains a function that will say the vector of samples and probabilities using a self-described binary format. And of course, there is only one that we saw, which is netcdf. So there is just one more file that you need to create following the function. It's very close to the function that we saw today at the beginning of the class. Basically, this function will save in one netcdf file these two vectors, so related to what I was commenting today about the list object that is being passed into the netcdf functions. Okay, and be sure to include proper metadata describing what the data is, who generated, why did you do it, etc. As I mentioned, as we just discussed, because you guys are needing some more extra time, I'm going to change this, and instead of having the assignment due on the 14th, it's going to be due on the 21st. Okay, sounds good for everyone? In any case, don't worry. The assignment I was planning to have for maybe assignment 5 or assignment 6, I can put it as an exercise. So if you guys want to practice more, you will have the chance to do so. Okay, I know that we are just looking at the assignment, but as usual, if you guys have any questions about the assignment, the details, just to let me know. Read this carefully. This is more than anything introductory text, not much detail about the assignment is given other than the motivation and the reason for applying this technique. But as I told you, I feel this is a nice assignment because it covers many of the topics we discuss in class, but also a very, very powerful technique in scientific computing in general. Okay, so try to be mindful about the steps while we are implementing, but again, the steps are not so difficult if you just concentrate in the particular details of each of the parts. All right? Okay, so any questions? I'm sorry I took a little bit longer, but I think we had a fruitful discussion in the middle at the end. So I'm going to remain in the chat for a few more minutes, but if you guys have any questions, I'm happy to take it as well. Okay, so looks like everything is quiet. As I say, I'm going to remain in the chat for 10 or 15 more minutes. You let me know if you have any questions about what we discussed today, and so on. All right, if not, I see you next week. Have a nice weekend, and again, let me know if you guys have any questions.